If you instruct an industrial manipulator to move from point A to point B without any further instructions, it doesn't fail quietly. It attempts the movement, vibrates violently, and often tears itself apart. The cause of this failure lies in the mathematical distinction between a path and a trajectory. A spatial path is strictly geometric. It is a sequence of three-dimensional coordinate points connecting a start pose to a goal pose, entirely independent of time. A trajectory assigns strict temporal limits to this geometry. It's a time-dependent description of motion. To successfully execute a movement, a trajectory must define three specific kinematic variables at every distinct instant in time: the position q of t, the velocity q dot of t, and the acceleration q double dot of t. Feeding raw target points directly to an actuator without generating temporal equations is impossible to execute, resulting in immediate hardware damage and system failure. Analyzing a step input command, charting position, velocity, and acceleration explains the failure. At time 0, position undergoes an instantaneous vertical jump. Since position changes in 0 seconds, required velocity spikes to infinity, causing acceleration to break its upper limit. Newton's second law dictates that force is mass times acceleration. In a rotational system, an infinite mathematical acceleration demands that the robotic joint apply an infinite amount of physical torque. Physical actuators possess strict limits on their maximum velocity and torque capacities. Requesting a step input forces immediate actuator saturation, generating massive transient errors and severe mechanical wear on the gears and linkages. To solve the infinite velocity problem, we give the motion a specific duration. The position graph now utilizes a linear ramp stretched over time period t. Consequently, the velocity graph maps to a flat horizontal line, operating at a finite, feasible speed. However, this linear profile contains a critical mathematical flaw. At the exact start and end of the motion, velocity transitions abruptly in 0 seconds. Calculating the derivative of these instantaneous changes produces infinite acceleration spikes at both t equals 0 and t equals t. These localized spikes demand impossible torque. The system attempts to comply, resulting in heavy, destabilizing vibrations at the start and end of every motion block. To guarantee safe physical execution, bounding the maximum values is not enough. The position, velocity, and acceleration functions must all remain mathematically continuous from start to finish. To achieve that continuity, trajectory planners use polynomials. The cubic polynomial is the foundational equation used to ensure continuity across both the position and velocity outputs. We define the exact shape of this equation using boundary conditions, the known physical constraints of the robotic system at the start and end times. The first two boundary conditions establish the geometry of the motion, the initial position at time 0 and the final target position at time t. We constrain the initial and final velocities to strictly equal 0. Plugging these constraints into the cubic equation solves for its coefficients. The position graph morphs into a continuous S-curve, and velocity becomes a smooth parabolic arc. The cubic polynomial leaves acceleration as a linear slope that jumps instantly, forcing an abrupt torque step. We eliminate this by applying a fifth-order quintic polynomial, setting initial and final acceleration to exactly 0. These polynomial functions act as a mathematical shock absorber. They seamlessly translate discrete spatial points into physically feasible continuous torque commands. While polynomials provide perfect continuity, safety-critical manufacturing frequently relies on an alternative method, linear segments with parabolic blends, widely known as the trapezoidal velocity profile. This chart shows a velocity curve shaped as a strict trapezoid, divided into 3 distinct temporal phases. The sequence begins with constant acceleration, smoothly and linearly ramping up the joint velocity. Reaching target speed, it enters the linear segment, coasting at a constant, predictable maximum velocity. Finally, a constant deceleration phase mirrors the initial ramp, bringing the joint to a precise halt. Because acceleration is held to piecewise constant values, the system never generates a negative velocity command. Engineers specify trapezoidal profiles in industrial robotics to guarantee the arm will never mathematically overshoot its target position. Generating a trajectory for a single, one-dimensional actuator is a solved mathematical problem. But scaling that logic to coordinate a highly complex 7 degrees of freedom manipulator requires a choice in how the system processes spatial geometry. The first architectural approach is task space trajectory planning. The system interpolates the target path directly in Cartesian coordinates, forcing the end effector to travel along a perfectly straight line through three-dimensional space. To adhere to that straight line, the computer must solve dense inverse kinematics matrices at every single micro-update, calculating the exact required angles for all 7 joints simultaneously. This imposes a massive computational burden and physical risk. As the arm maintains the strict Cartesian path and approaches kinematic singularities, individual joint velocities spike erratically to keep the tool precisely on track. The alternative is joint space trajectory planning. In this model, the system solves the inverse kinematics strictly twice, once at the starting waypoint and once at the final target. The computer then interpolates polynomial trajectories directly on the individual joint angles. This bypasses the continuous matrix calculations, drastically reducing the computational load and guaranteeing perfectly smooth, continuous actuator motion. But prioritizing the joint space sacrifices spatial strictness. Because each joint accelerates independently along its own polynomial, the physical path of the end effector deviates from a straight line, sweeping through the workspace in a wide, unconstrained curve. Motion planning requires engineers to constantly weigh these factors, the operational demand for strict spatial predictability in task space, against the computational efficiency and actuator health provided by joint space. If we map the overarching architecture of robotic control, trajectory generation serves strictly as a translational middle layer, sitting between user spatial inputs and low-level hardware control. A human operator or a navigation algorithm provides raw Cartesian coordinates, but without a strict timeline, those target points are physically meaningless to the hardware. Low-level feedback controllers, like PID loops, constantly track position to eliminate transient errors during motion. They can only maintain stability if the reference commands they track are continuous and physically feasible. Whether utilizing cubic polynomials or trapezoidal blends, trajectory planning generates those feasible commands. Ultimately, it is the mathematical discipline that bridges the gap between theoretical spatial intent and physical mechanical reality.